Hi, good afternoon, uh, and welcome back to the second last class or week 11's doubt clearing session for aluminum based alloys and metal matrix composite. I am Ananya, I am a PhD student at IIT Delhi. Let's start today's class. So this week lectures was basically around the fracture behavior of metal matrix composites. In week 12 lectures also you will find the fracture behavior of metal matrix composites only. So in metal matrix composites we got to know about the fiber reinforced and particle reinforced metal matrix composite types. So first of all, there can be ductile fracture or brittle fracture. So first you should understand what is ductile fracture and what is brittle fracture, how they behave under the fatigue condition. So here basically we'll be talking about the fatigue fracture. It's somewhat different than the tensile, the UTM fracture. So let's start today's class. If you have any specific doubt, you can ask. Otherwise, I'll go with the topics of week 11. No doubt?
No, ma'am.
Okay, I'll share my screen and we'll discuss about all the topics of week 11 one by one. Uh, so the first topic was the fracture behavior. So in the last class, we got to know about the dislocation mechanism, how the dislocation can move inside the composite. So there we got to know that the interface between the particles or the reinforcement material and the parent material is very crucial or critical, because at the at the interface the fracture may happen. The dislocation density will be very high in the interface. That interface is a critical zone. Again, I'd like to have a recap. Like in alloy, if this is an alloy, if this is the lattice, inside the lattice the alloying element will sit. But in case of composites, the composites sit like this, and they will have a interface bonding with the material. So it will look like, if this is the particle, this is the interface, and this interface is connected with the parent body of that matrix, and in the interface the dislocation density will be very high. High dislocation density, rho is the dislocation density, and this interface is the critical zone. So there can be two types of cracks present inside a metal matrix composite. So crack means, I have talked about some grains, grain boundary and grains in case of alloys, right? If this is the grain, these are the grains. Then in between the grain there are bonding. Okay, grains means the lattices are oriented in a particular direction in one grain. So when they are oriented in a particular direction, that will be considered as a grain, and in the subsequent one the lattices are differently oriented, but there will also always be some bonding in between two grain. So these grain atoms and these grain atoms are connected with the lattices with the atomic bonding. But what happens in case of crack? Crack means somehow this bonding has been broken. So breakage of the bonding signifies as a crack. So this is the atomic level crack. When this cracking happens, it will propagate. And also, if cracking is happening, means there is some externally applied load, due to which the cracking is happening inside the material. So due to some kind of tensile force, if this cracking is happening, means uh, this along this line, all the atoms are not connected with each other. So this is why this is called as crack. This is the bonding, okay? And in the end of the bonding, at the end, there are atoms. Previously these atoms were connected like this. Previously it was like this, but now it's not like this because one cracking has taken place. So this is cracking. So when these cracks propagate, they will take a larger shape and size or geometry. We'll observe a crack under the microscope in the parent material. In case of alloys, this crack will be just normal thing because the alloying elements basically sit in the interstitial, in the substitutional position. But in case of metal matrix composite, the composites are having a different set of lattice, a different set of what should I say, reinforcement material with a different lattice orientation, lattice type and everything. So this is why in metal matrix composites, cracks can be of two types. One crack can be like a crack which is propagating through the matrix. It's not bothered about the reinforcement particles which are seated over there. And another crack is like if there are particles, in between the particle there are crack, or if there is some fiber, in between the fiber there are cracks. So these two types of cracks can be present in case of composites. This is composite crack. This is matrix crack, and this is reinforcement particle crack, or reinforcement crack I'd say, because there can be particle or can be fiber. There cannot be both at a time, but just for the sake of understanding, I have drawn the like this. So, in case of fiber reinforced composites, the material flow in case of the UTM or fatigue or any type of testing, at the time of testing, there will be some material flow in a particular direction along the direction where load is applied. That part or material flow, when it is in plastic region, means the material is flowing in a particular direction. Flowing means there is a elongation in a particular direction, and that will not get revert back because that is in plastic zone. There, that type of elongation, that plastic elongation can be seen in case of ductile fracture only, because we know if I draw the normal stress strain curve, then this thing will be seen in case of ductile material only. It cannot be seen in case of brittle material. But brittle fracture, then it will get the breakage. In this part, there will be necking and then the fracture. But the brittle fracture goes like this. There will not be any plastic region. But if we are going for fatigue test is somewhat different than normal tensile or compressive test. So I'll be talking about that. But before that, if we are going for normal tensile testing, what may happen is if there is one crack due to the test or not due to the test, whatever it is, if there is in this direction, there is some tensile force, this crack will be broadened, huh, and the tip will be blunted. So blunting of teeth will take place, and this is common phenomena, happens everywhere, because this is for the matrix crack. It is common for the alloy as well. But in case of fiber, what may happen is if I consider the fiber or the particle as a separate entity, then just consider the particle here or consider the fiber here. do not consider the matrix here. Then if this is the fiber, somewhat like this type of load is applied, so this fiber can get separated by two halves because of the breakage or the particle. So there can be like particle breaking. Okay, but these things are not a separate entity, not a separate entity. They are connected with the matrix. There is an interface between these particles or reinforcement particles and the matrix. So what will happen? What will happen then? There will be a, an effect of the load that has been applied at the interface. If the interface bonding is very high, it's strong, then the interface will be as it is, but the particles will get broken. If the interface bonding is not very high or very strong, it's weak, then the particles will get separated from the matrix. That's what happened in case of ductile and brittle fracture respectively. So if there is a matrix and there is one particle and the interface is very strong, then at the time of testing, what happened? It will sit and it will get broken down and two halves will be separated maybe, but they will still be connected with the matrix. And in case of, and this is ductile fracture, but in case of other type of fracture, what is basically observed is the interface which is weak. What will happen? This particle will just get separated. It will sit over somewhere else. It will just sit. It will not be connected with the matrix anymore. So there will be considered as a they will be considered as a separate, not connected or not bonded loose particles, and this thing will be called as brittle fracture. So the fractographic plane and the images were shown at the time of class. Those images are not with me, but if you remember, there will be some dimples created in the case of ductile fracture. This type of holes will be created. So these are basically due to the fatigue testing or just the tensile compressive testing, and the particles got separated from the holes. So this was the hole previously where the particles were seated, but now the particles are separated from the matrix. So these are the empty holes there. So you will see this type of features in case of metal matrix composite when you expose it under the fatigue fracture. So the yielding of the matrix at the broken edges will relax the stresses and will prevent the crack from propagating. The result of which is the blunting of the crack tip. So obviously if there is a crack in the matrix and you are just still applying the external load, the crack will propagate or the crack may propagate, and due to that broken matrix, there the broken part or the crack which is present there will relax the stress, will, in simple language what we can say is, if there is a crack and if I am applying the load, still I am applying the load and the particles are present over here, there is no crack in the particle, what will happen? This thing will be broadened up, and as a result the particles will be as it is. There will be no harm in the particles, but the crack will propagate a little bit in the matrix, by which it will relax all the stresses which has been applied, and the blunting of the crack tip will happen. As a result, the crack will not propagate anymore, because if this is blunt, this is a blunt tip, the crack will not propagate, because to propagate the crack, it should have a sharp tip which will propagate easily throughout the matrix. Because as I said, crack means these debonding of particles, debonding of the atoms of the matrix. So this was about the ductile matrix or ductile failure. When the matrix is ductile in nature. So this is basically failure of ductile matrix. If the matrix is brittle, then what happens is the matrix will fail very easily, and as a result it will not have a strong bonding with the particles or the reinforcement materials. As a result, if there is a externally applied load, the particles or the fibers can easily get separated from the matrix. They can get broken and separated as well. Both the things may happen, and they will fail very easily. This is one thing. But growth of the crack is also important in case of these two phenomena, because in case of ductile, the growth of the crack or the propagation of the crack will not happen that much if the blunting has taken place. But in case of brittle, the growth is large or larger than ductile, and it will just propagate very easily and rapidly, and will go up to the rupture point. So after that, from lecture 2, the continuously reinforced composite and the discontinuous reinforced composites were discussed. So if there are the fibers or the particles, whatever it is, there can be strain developed due to the externally applied load. So due to the strain, sometimes what may happen is work hardening. We know for work hardening, we sometimes go for strain elongation with a very high strain rate, where due to the high strain rate, the alloying elements, which are also called as solute atoms, get a easy path to move from throughout the lattice, but the dislocations will feel difficulty to move at that short period of time. And what happens is, the particles will, the alloying solute atoms will sit as a atmosphere, and they can do the work hardening for them. So this type of phenomena may also happen if you are exposed your material to some tensile or compressive uh, forces, externally applied forces. So what may happen is, if you are exposed your material to some tensile test, work hardening may happen, or fracture may also happen. So fracture is something which is denoted by the, or which is attributed by the weakening of a material, and work hardening means the material is getting stronger. So these are two absolutely opposite phenomena which may occur either way or simultaneously. So then if they are taking place simultaneously, then we can say the dp, with the load which is experienced by the material at the time of tensile testing, is zero, because there are two opposite phenomena taking place at the same time. So due to which there was one derivation. I'm not going into the derivation part. The instability load or instability in tension was derived like this. This was the equation of instability in tension loading. Also, strain hardening, if it's taking place, then it will take place following the power law. So there was some equation where we had a graph like this, where, sorry, two phenomena is taking place, and this was the instability point where this equation is valid. So this was the thing. Then we were been discussed with the crack propagation, how it happens mainly inside a normal material. So
Excuse
yes,
me,
please.
ma'am.
Yes, please.
Excuse me, ma'am.
Sorry for interruption.
Yes.
Ma'am, could you please explain the graph once again? Because
Okay.
I didn't get the point like epsilon u. The intersection point, actually, I am not able to put it.
Okay.
Just
So
the graph, not the
okay, okay.
equations that I
Yeah.
don't have.
So if this is the graph of stress strain, normally it will go like this now. But if work hardening is taking place, so it will be like the strain is increasing, the stress is also increasing. But here with the strain, the stress is decreasing because work hardening is taking place. Means the load, the stress which is experienced by the material is going down with elongation, with the tensile test. So this is why this graph is going down. And this point of interception is called the instability point. When because these
Ma'am,
two graphs are interacting with each other and they are uh, yes, you ask whatever you are asking.
yes, ma'am. Actually, the strain is increasing and the stress is decreasing. So this phenomena we have seen in dynamic strain aging. So that's what you are discussing.
Yes, yes, yes,
Okay, so in this phenomena, we can assume like dynamic strain in
yes,
which the solute atoms is already seated
yes, yes,
over the dislocation, right?
yes,
Means there is some opposite phenomena that is happening like in dynamic strain. There is some inverse phenomena that we are seeing,
hmm,
right?
hmm.
Okay. Okay.
Okay, okay, okay. So yeah, that was called as dynamic strain aging. Here it is called as work hardening. Both the things are same. It's like you are applying the load. The strain rate is basically so high that due to the high strain rate, some temperature has been increased inside the material, due to which that increased temperature is acting as a thermal activation to the solute atoms, and the solute atoms are going very fast this time, but the dislocations are not getting enough time to move inside the material. This is why the solute atoms will rapidly move and will sit in front of the dislocation, and they can form some atmosphere where they will not get bonded to each other, but they are having a less attraction for with each other, that they are just making some cluster, and that will restrict the movement of the dislocation. And this is what we been taught in the case of dynamic strain. So this is what called as work hardening. So both the curves are opposite. So due to which when they are meeting at a certain point, that is the point of instability. At that point, the material will be very unstable because it can go in this way or in this way. So it will be a confusing situation for that material at that point. So due to which it's called as instability point. Instability point. So after that,
Yeah.
yes.
All right, ma'am.
Okay. Okay. So after that, it was taught all those equations were there, but apart from that, there was the phenomena how the crack is propagating mainly. So as I said, na, when you are doing some tensile test, so if you see look at it in a microscopic scale, what you'll see some grains are there, grains like this. There can be some small grains, some larger grains, something like that. So when you're applying some load, these grains will be elongated. Grains means now grain matlab kya hai? The lattices which are oriented at a particular manner. अब lattices matlab kya hai? मतलब the atoms which are bonded with each other, and this bonding direction is in one way, one along one direction. So the grains are elongated means this bonding is getting elongated. From this picture, it's something, it's going like this. These are elongated. ना देख के समझ में आ रहा है. कि थोड़ा elongate हो गया सारे bonds. So this is what meant by grain elongation. After certain time, you can tell by yourself only, these bonds will be broken. There will be breakage of bonds because after some time they cannot sustain that elongation after some time, because elongation means the atom bonding means the atoms are sharing some electron with each other and they are getting bonded, and after some time there will be a larger distance between two atoms in such a way that that electron sharing cannot happen anymore. So there it will look like this. So there is a breakage, and due to this breakage, some voids will be nucleated. So firstly, the crack will not getting generated because crack means there is a huge number of bond breakage, atom breakage, atom misplaced, these things. A huge crack means. But first, these bonds will be broken, and due to the breaking, there will be voids which will be generated. Void means empty space, because this is a empty place. This is one empty place. Previously there were some atoms here in this picture. You can see there was some atomic arrangement, but now between these two bonds now there is nothing, so there are some voids. This void is now in an atomic level, that is in nano level, but after some times when you are applying the load, these voids will be nucleated. These voids will be spread over the whole lattice, and the voids can be in any position, and when these voids will but these voids will be present at the weakest position of the lattice, so of the material. So if this tensile sample is like this, so this is the weakest position of the tensile sample. So obviously we make it we actually knowingly make it just to get that weakest position in at the middle so that calculation may easy ho. So this weakest position is this. So all the lattices, all the grains present over here will have that voids. In this whole position also there are millions of atoms. So at the middle position, ideally at the middle position the void nucleation should start, and the voids will be nucleated after some time. These voids, if there is, these voids are adjacent to each other na, so they will make a larger void. Somewhere it's a smaller void. After some time these voids will be nucleated, will be coalescent with each other. So coalescence of void will take place, and then this void will take a, picture of the crack when this void is larger uh, enough. Then this crack will propagate obviously because we are still increasing the tensile load, and after some time there will be breakage of the whole material by the void nucleation and crack propagation. So this is the normal phenomena of any type of cracking. In case of ductile fracture, the plastic zone will be much larger, so means there will be much more elongation in the material. The grains will be elongated a lot. After some time when they cannot sustain more, they will have that voids and nucleation and the crack. But in case of brittle, the grains cannot elongate more. So this is why there will be this void generation, and these things will be so fast that you cannot even recognize between these steps, and it will just get the mm, fracture. So in case of ductile fracture, there will be necking. Necking means where these things are taking place, these things. So if this is the tensile sample, voids are there. These are nano level voids. Then these voids are getting coalescent. Then these are making some bigger voids. Sorry. Then these voids are making some cracks, and if one crack is getting some favorable condition, it will propagate and it will go up to the uh, rupture point. So this is how the ductile fracture takes place. The brittle fracture will also have these things, but it is so fast that you cannot recognize. So there will be no necking. This is called necking. This is a specific phenomena for ductile materials. So this is what was taught up to lecture 2. If you have any doubt, you can ask. Otherwise, I will go to the lecture 3. Okay. So from lecture 3, again the fracture behavior was continued. So there was two mode of nucleation, the particle cracking and the decohesion. Decohesion means decohesion at the interface. Means the interface bonding is not that much. So decohesion is taking place. So the particle cracking will be a symbol of ductile fracture of the composite. So this was for the parent or the matrix. If matrix is ductile, matrix will fail like this. If matrix is not ductile, means matrix is brittle, matrix will fail like this. But now we are talking about the composite, so where the reinforcement material is also present. So what will happen? There will be a critical and crucial point which we should understand and consider uh, about the interface of the reinforcement material and the parent material. How the interface will act. We know how the matrix will act. We know in almost every cases the reinforcement particles are brittle in nature. This is why we are mixing it with the matrix, because in case of aluminum is a ductile material. So obviously with same ductility we will not reinforce any material to it. So it should have always a better brittlity than the aluminum alloy. So there the fracture of the particle will always be, or in most of the cases it will be kind of brittle fracture. The particle, reinforcement particle will have brittle fracture. Aluminum will have ductile fracture. But what about the interface between these? How the interface will look like at the time of fracture? So there can be two phenomena. One is particle cracking, another one is decohesion. But before going into that, I have a question. So did you guys get any mail regarding the extra classes that is going to happen tomorrow?
No, ma'am.
Okay.
No, ma'am.
So okay, so there will be an extra class tomorrow from 5:30 to 7:30, but it is not confirmed yet. This is why maybe you haven't got any mail yet. But if you get any mail, it's fine. Otherwise, I'll also get the mail where the extra class will be. So
Ma'am, like that tomorrow's class will be the last class.
yes, no, the last class will be on 17th, the next Tuesday. That will be about the
Okay,
week
okay.
12 lectures. This is like the normal classes. This is for week 11, and the 17th class will be on week 12. But in between these two, or after these two, I was supposed to take, actually I was asked, so I told that yes, an extra class will be easier for me to recapitulate all the lectures, because there are a lot of topics which has been discussed in this particular lecture series yet. So to have a recap class, we'll have the class tomorrow. So you try to recapitulate all the topics that has been discussed in this lecture series. Otherwise, I'll go with all the top. I cannot go with all the topics, but I'll try to cover all the topics in tomorrow's class. If you have any specific doubt regarding this aluminum alloy and metal matrix composite, write it down. You can ask me at the time of class, or you can ask me via mail as well. I'll try to solve it. So this was the small announcement. If you are not getting the,
Excuse me, ma'am.
yes.
Ma'am, I'm sorry to interrupt, but is it possible that we can either do it tomorrow towards a little night or maybe on a not working day?
Not working day. Okay. Actually, I was asked for the day, so I have already filled up the form for tomorrow. But you guys haven't received any mail yet, so I don't know whether it is confirmed or not. But day after
Ma'am,
that,
like even if the class happens tomorrow, its recording will be available in the
yes,
portal. So,
yes,
like,
yes.
if somebody has any doubt in case he or she is not able to attend the live class, they can ask on 17th. So,
Yeah, that is fine. But if someone wants to attend the recap class, so okay, I'll actually I am having my own classes and work in the weekend, so that's why I couldn't reschedule it after 17th.
Yeah, ma'am, I understand. Ma'am, actually, I have classes till 6 o'clock in the evening and
Till
every
6.
day.
Okay, okay. So after 6 you can join, I think.
Yeah, ma'am, I'll try to join tomorrow.
Okay, okay. So we can do one thing. We can start our class from 6 tomorrow.
yes, ma'am.
Yeah,
Yes,
ma'am,
ma'am.
that would be helpful.
But I am not sure yet whether the class has been considered or not. If they consider the class that I have proposed, then only the class will take place. So if you get any mail by tomorrow, it will happen. Otherwise, you'll get the further mail, I think. No issue. Whatever mail you get, the same time I get the same mail only. So, okay, let's see what happens. So, that will be a recap class. And the 17th class will be the last class for week 12. And if you have any further doubt. Okay, so let's resume the class. So, I was talking about the two mode of failure for the metal matrix composite, which will be a slight different than the normal matrix failure or the particle failure. I have already discussed that the interface, if the interface is strong enough, then one thing will happen. If the interface is weak, then one thing will happen. So somebody tell me, if the interface is strong, what will happen?
Ma'am, if they
Actually, yes, continue, sir.
Sorry, I couldn't. Can we repeat? Can we repeat?
Ma'am, actually, if interface is strong means there is a ductile fracture. There is no decohesion which is present. So there will be cracking in particle, and there will be a ductile fracture in the material.
Yes. So if the interface is strong, means the crack, the what's it? Uh, the failure will be ductile type of failure for the composite. So there are different things. Okay. So the matrix can have a crack, and the crack propagation in the matrix, how it will take place, it depends upon the matrix type. But whether there is a ductile, the whole setup is ductile or not, that depends upon the matrix as well. If the matrix is ductile, obviously the particle will be bonded to the matrix with a stronger bonding. If the matrix is brittle, then the particle will get weaker bonding with the matrix. But at the same time, there is a resultant property of the composite. That's why we use composites rather than alloys some applications. So even if the matrix is ductile, it may happen that the particle is so strong that it is not having that much stronger bonding that was supposed to be. So the whole combination now I'm talking about. So the whole combination here is ductile type, where the bonding is very strong. So there what will happen? The bonding will not break, but the particle will break. So this is why I am telling that this, so there is a matrix, there is a particle. So you can imagine in case of brittle fracture, what happens is there will be a sudden breakage in the graph or in the material. Means the grains which are present inside the material, the atoms which are present inside the material is having debonded. The grains are having debonded with each other, and there is a sudden crack propagation and failure. But here the particles are brittle. So there will be a sudden breakage in the particle, but the interface is still not breaking up. So it's type of mixed up properties. This matrix is ductile, means this matrix will elongate, but it's having so much strong bond with the interface with the particle that when it will elongate with the particle, but the particles are brittle, so the particles cannot get elongated, so they will get broken down. Then it will be exposed to the load. What will happen? It will get elongated, the matrix, and as a result this interface will not break, but the particle will get break. So this is a very interesting topic, that a ductile material is having so much high strong bonding with the particle that the interface is not breaking. There is no necking or void coagulation in the matrix in the interface, but the particle is breaking down. So this is what been taught in the lecture 3. Some pictures were shown. I don't have the pictures with me right now. So the void growth and coalescence of void, these things may happen in the matrix if the matrix is ductile, but the interface will be so strong that still the particles will be seated over there. Because in case of brittle fracture, if the particles are getting debonded, previously it was here but now it is here, so obviously it is not bonded anymore. It is just like a loose particle inside the matrix, which is a bad thing for the composite, because we are using the composite because of its interface, its energy and its strength. So again, depending upon the application, we choose the matrix and the particles or the reinforcement material. In lecture 4, the fatigue was introduced. So in case of tensile testing, we can understand its simple phenomena, how this breaking and breakage of things are taking place. But in case of fatigue, this is something different. In case of fatigue, it's a type of fluctuating load. So if this is time and if this is load, with time the load is increasing. This is normal tensile testing. But if with time, if the load is increasing, then decreasing, then increasing, then decreasing, this is a fluctuating load. And this is what happens in case of fatigue fracture or fatigue testing. So fatigue means there is a repetitive load like sinusoidal load, where the similar amount of high and low stress is being applied. This high low value can be similar with opposite sign and can be different as well. So it can be like this three type can occur. This is the zero. So the stress range is maximum minus minimum, maximum stress minus minimum stress. The mean stress is maximum minus plus minimum by 2. The amplitude of the stress is the maximum plus minimum by 2, somewhat like this. I don't remember the exact equation. Now you tell me, okay, the stress ratio was minimum by maximum, I think. Minimum by maximum. This was stress ratio, which is very important in case of fatigue stress testing. Now you tell me in which of these cases, this is 1, this is 2 and this is 3, where the R will be minus 1.
Ma'am, in case of completely reversed load,
In the
like in
pictures
case
you tell.
two, in case two,
In case of 2, yes. So where the R can be 0.3,
it is for case one. The stress is more.
so 0.3 means mean by max is 0.3. So max into 0.3 equal to mean. So some maximum stress is multiplied with 0.3 and we are getting minimum stress. So both are positive, but the minimum stress is lower than the maximum, obviously. So it will be like the 1. And in this case, the R value, tell me.
Ma'am, in this case, our value is positive.
R value will be positive. What will be the value?
Means it is in fraction, like minimum is always less than maximum, but it is greater than zero.
It is greater than 0. Anyone else? Other people can also
Ma'am,
participate.
ma'am, you are asking about one or three?
3.
Okay, in three it is zero.
Yes, in 3 it is 0. In 1 we have derived if it's 0.3 or zero point 0.4, whatever it is, something R value less than 1. So in 3 the minimum value is 0. So obviously the R will be 0. So this is what I tried to show, because for different R value we'll see different graphs in the subsequent lectures. So this is why I have shown. Then uh, this is about the fracture fatigue load that can be applied. Then the stress. So fatigue limit, or fatigue, when the fatigue load is applied, it will tell us about the fatigue life of the material. It can be low cycle fatigue or high cycle fatigue. Now, what are these two? Fatigue means fluctuating load. Now, if I am applying some fluctuating load to a material, now there will be two questions. For how many cycles I am applying? So, if this is one cycle, and this is two cycle. So there can be a lot of cycles. So how many cycles for which I am exposing the material, and how much load I am applying at the time of fatigue test. So this cycles will have an amplitude. So how much will be the amplitude and how many cycles I will carry on. So depending upon that, there can be low cycle, two type of fatigue life, can be two type: low cycle fatigue and high cycle fatigue. So low cycle fatigue, as the name suggests, low cycle fatigue means number of reversals or number of cycles will be low. Number of cycles will be high in case of high cycle fatigue. If the number of cycles are low, now you imagine I have a material, I am exposing it to a fatigue test, and after 10 or 20, low cycle means it's around 10-20 cycles. So after 10-20 cycles, it's failing. We don't have a use of that material, because if the material we are going for fatigue test means in real time application, the material or the component is going to experience that type of fluctuating load. That this is why we are going for fatigue test. And if it is failing after low cycle, after 10-20 cycle, then that component is of no use for me. So why I'll go for low cycle? It's not like that. It's like for low cycle fatigue, we increase the stress and we see for high stress how many cycles can be sustained. Because obviously if we increase the stress amount or the amplitude of the stress, the number of cycles will be lesser. This is why we are going for the low cycle. But high cycle means somewhere where I am going to use the material for a particular component, there the component will be exposed to some fatigue application, fatigue loading, but the fatigue stress will not be that much. So why I'll test the low cycle fatigue? I'll go for high cycle fatigue, means the stress will be lesser, but for the long time, the low stress, the low fatigue stress will be or the component will be experiencing that low stress in a repetitive cycle for high time. So obviously we'll expect a longer lifetime of that component. There we'll go for the high cycle fatigue. So it's not like you'll always go for the low cycle or always go for the high cycle. It depends upon the application where you want to use your component of a particular material. It can be metal matrix composite or analog. So this is why we go for low cycle fatigue or high cycle fatigue. Low cycle fatigue deals with a lower number of uh, cycles or number of reversals with high stress. So if it's like this, so there the number of cycle is low, but this is stress amplitude and number of cycles to failure. Means up to failure, we go up to the failure point and see how many cycles the material or component can sustain before failure at that high stress value. So there the amplitude is very high and the number of cycle is low, but here the number of cycle is very high, but the stress is low. So this is representing the high cycle fatigue and this is representing the low cycle fatigue. But there is one mean stress. So the stress amplitude can be different, or the stress amplitude can be constant, but the mean stress can be different. Mean stress means maximum plus minimum by 2, and amplitude means maximum minus minimum. I cannot say, but it's like this thing. So it depends how the cycle is looking like. So the amplitude can be constant, but the mean stress can vary. So for different mean stress value, means for different these cycles, one cycle, two cycle, or three cycle, or four cycle, or five cycle, different cycles I am exposing the material to and seeing how the fatigue life is going on. So the graphs look like this. Number of cycles, it can be considered as 2n, and this is sigma A. and where this is like. So here the mean stress is lesser or the least, where the number of cycles to failure is very high, rather than the mean stress, which is very high. So obviously the number of cycles to failure will decrease. So it's a kind of common sense you can apply. If you are increasing the stress, obviously, even if the amplitude is same, but the mean and maximum value is, you are increasing the mean maximum and minimum value. So obviously the number of failure will decreasing will decrease. So then the R value. So if now the mean stress I am comparing for log n, because there is one relationship like this, and now I'm plotting log n with mean thing. So there with R, with different R, this thing will change. So these are pretty easy calculation, and the graphs, normally also you can understand without any equation, that if you are increasing the stress, obviously the number of cycles to failure will decrease. If you are decreasing the stress, if you are decreasing the stress, the number of cycles to failure will increase. And depending upon this phenomena, we have divided the fatigue or fracture thing in two parts: low cycle fatigue and high cycle fatigue. For low cycle, the stress is higher. So the stress is higher means when you are exposed, you are exposing the material to the low cycle fatigue. Due to the very high stress, the temperature will also increase inside the material, and there will be thermal stress developed as well, along with the mechanical stress. And the thermal stress will lead to more and more strain inside the material rather than the mechanical stress, and due to which there will be a larger deformation or strain, you can say. Even if there is no deformation, there will be larger strain, and uh, which you can control basically, and the number of cycles to failure decrease. So this, using this phenomena, or using the concept of low cycle fatigue and high cycle fatigue, researchers have discovered two type of tests. One is strain control test, another one is stress control test. So it's like, as in case of low cycle fatigue, the stress is very high, the applied stress is high, and over that the thermal stress is also developing. So the strain is controlled, but the stress is very high, and you cannot control the stress here because the thermal stress is not in your hand. The externally applied stress is in your hand. So you are applying some certain level of stress, and the thermal stress is also developing inside the material. So due to which we go for the strain control method in case of low cycle fatigue, where we can control the strain depending upon the stress we are applying, but we cannot control the stress which is developing inside the material due to the externally applied stress. So up to this point, do you understand this thing? Anyone? Or if you have any doubt, you can ask.
Ma'am, this is Baskin's equation.
Can you repeat? Your voice was cracking.
I'm saying this is Baskin's equation.
Yes, yes, yes. So, what I tried to say, let me write it down. If I am applying high stress, then the thermal stress will develop inside the material, and the strain will also develop, but it will not be that much, because in case of fatigue, we are not really increasing the stress. We are concerned, we are more interested with the stress that we are applying. So this thing is in our control. We can control the strain, but this thermal stress we cannot control, because this thermal stress is the result of the stress that I am applying. So this is why this strain I am taking help of. So I am taking help of the strain, and I am calling it as the strain controlled method or strain control test for the low cycle fatigue. I am doing the low cycle fatigue, but I am calling it as a strain control test. Whereas for high cycle fatigue, the stress is lower. So as a result, there is no thermal stress, obviously, there will be strain. But this stress is lower, so I am controlling the stress here. So it will be stress controlled test. So using this concept of strain controlled and stress control, we will go for different types of fatigue testing. So there was one graph. Obviously, when you are doing the fatigue test, maybe the load can look like this, exact similar cycles with each reversal, but the material which has been exposed this type of fluctuating stress will not experience or will not behave the same way with each reversal. Because if the grain was this and now it is elongated, and with the compression it will not look like this, it will look something else. It may happen that this elongated grain cannot recover its original shape or size, it will be somewhat like this. So it's never possible that the same way, it's not a reversible equation, okay? It's irreversible. So this is why there is a hysteresis loop. The loop is not with the exact, means if I am applying the stress and I'm applying tensile stress and applying compressive stress, the same way the material will not go back. The material will go back following some hysteresis loop. And Bossinger effect, which is called, so there is one strain which is falling under the elastic region. There will be some strain which will fall under the plastic region, and depending upon these two, plastic and elastic strain, will get the total strain. So in this case, we will control the total strain if this is the material. So here it is plastic region and this is elastic region. So up to certain point, when we are applying the external load, we'll have a elastic strain. After that, we'll have the plastic strain, and due to which, when you revert back with the same path of the fatigue fluctuating load, you'll have the hysteresis loop. So this is the total strain, which I am controlling in this case. So total, okay, total strain I'm controlling. So this is elastic plus plastic, and this thing I'm controlling because it's strain control. So I'm more interested in this one to control this. Then after some time, if I am varying the load, so if previously this was like this and now I am varying the load, So it will be something like this, and after some time I am again varying the load. So I am having different load, and I am considering the strain that is being generated, which is also I am calculating the strain, but I am just controlling the strain and increasing the stress and seeing that what is the result because of the thermal stress which is being generated inside the material due to the externally applied stress. There you'll get a graph like this. Which is also known as Coffin-Mansion relation, given by this equation. N dash is, okay, there is another equation which is called as the cyclic strain hardening equation, because due to the cyclic stress also we are applying some strain actually and we are getting the stress. So there the dynamic strain aging or work hardening may also take place. So there if I consider the hardening part, because when you are applying the fatigue uh, load or fluctuating load, up to certain point you can have the strengthening or hardening effect. After some time you will have the cycles to failure only. So if you consider the hardening portion, there will be this equation, similar type of equation, power law type. It can be called as power law as well. So where the K dash is the cyclic strain coefficient and N dash is the cyclic strain hardening exponent. So using these two equations, you basically get this type of hysteresis loop and the graph and the normal hysteresis loop as well. So this was all about the strain control. In the subsequent lectures of week 12 also, you will see this type of strain control and more brief, means more explained concept on the strain control and the stress control fatigue test. So let's go to the last lecture of this week, which is the fatigue crack initiation and the growth. So when you expose the material to one tensile test under tension or compression test, you are applying only one way uh, load or stress. In one way, the strain is happening. In one way, the grains are getting elongated. In along that direction only, at a particular weakest point, the voids will be nucleated. Those will be coalescent, and then the void growth and crack propagation, all those stuff will take place, and ultimately the fracture will take place. But in case of fatigue, there will be fluctuating load. So we are applying tension and then compression, then tension, then compression, and also for a very short duration, not like tensile testing, or it can be for long duration as well. Whatever it is, the duration will be constant for each reversal. Then what will happen? When you will expose the material to the tensile testing, the slip plane will try to move because the elongation will take place. So elongation means movement of dislocation. Movement of dislocation means the dislocation will move along the slip plane and direction. Thus the slip system will move. So when the elongation is taking place means the slip system is moving. So we can consider the picture like this is one slip plane and this is being elongated. This is the material you consider and this is been elongated. So in the material there are some slip planes and there are some normal planes as well. These planes will be elongated, and what will happen? The slip plane may go like this. So it can go like this. So the one slip plane has progressed a bit. With the next reversal cycle, it will try to go back. If it's in elastic region, it will come back. But if it's in plastic region, it cannot come back. So there can be two possible cases. If it has come back a little bit, it will look like this. And there are a lot of cycles. With each cycle, obviously, there will be different slip plane movement, and due to which what happens is the result is somewhat like this. This can be like this, or this can be like this. So this is what known as intrusion or extrusion. The slip plane movement in such a way that some planes have progressed a bit, or some planes have moved in an opposite direction, something like this. So intrusion and extrusion again have different effect on the fatigue life. If there is intrusion, this inside movement is called as intrusion. This is how you can remember. And this outside or exit movement is extrusion. It's like exiting. This was the previous case, and now it's exiting from the material, so it's extrusion. Here it was the previous case, now it's going inside the material, so it's intrusion. So in case of intrusion, a notch is created, and that notch can work as a stress razor. The crack formation or crack form preferable site for crack formation can be there, means this intrusion can work as a stress razor and crack formation initiation site. So this is one effect of intrusion and extrusion over this thing. If extrusion has taken place, extrusion will also have some effect, some striation inside the material, but it's better than intrusion. Then slip band can take place, and those slip band which has been uh, this intrusion and extrusion has occurred to the slip band, the crack growth will take place. Deepening of the initial crack can happen. If there is no crack, the void nucleation and crack growth can take place. And if there is already an existing crack, then crack propagation may take place, because the tip sharpening may take place, and if the tip is sharp enough, then it will propagate through the matrix. So the crack growth also has three different stages, 1, 2, and 3. So the graph looks like this. So there is one stage, second stage, and the third stage. So this is the crack. This is stress intensity factor, which is again very important in case of fatigue and fracture. And this is the, what is it? Someone tell me.
Actually, this is crack growth rate.
Yes, crack growth rate. So A is the crack length, and N is the reversal, number of reversal, you can say. So with number of reversal, how much the crack is propagating or growing, that is known as the crack growth. So this crack growth may take place due to the intrusion or extrusion. But it's not always true that only the sharpening of the tip will take place. A blunting of tip may also take place, because it's not a plain matrix or alloy, it's a composite. There the interface is also taking part in the fracture, and there are some particles as well. Where the crack is growing, if at the middle some particle is there, seated over there, then the crack may not grow, or it will grow, or it will just overcome the barrier of the particle. It may not overcome, it will get a blunt tip at the end, every possible thing can happen. So here, due to the intrusion and extrusion, as I said, some striation occurs which will be seen from outside in your naked eye in the fracture surface after the fractic testing. Like the serration, we talked about the serration in case of the dislocation movement, where the dislocation was gathered, there the serration was taking place. So similar thing in striation also, those type of lines will be present in the fracture surface, which you can see by your naked eye. Then if the striation is taking place, means the crack is there and it's propagating. The intrusion extrusion is taking place. So there the crack can grow like this. If this is one crack, it will grow like this, or it will grow like this, and it will get some blunting effect, or it will get some sharpening effect. So when the load changes to compression from tension, the tip direction changes and the crack face collapses. And this is why in case of normal tensile testing, if this is the material and it's having a crack in this, and the along this direction the tension was applied, tensile load, the crack will grow and it will have this effect, fracture. But in case of composite or in case of fatigue testing, we are giving the tensile and then we are giving the compressive, again tensile, again compressive. So the blunting effect is more, and also the faces of the crack which was present, which was propagating at the time of tension, will get collapsed at the time of compression, because it's just the opposite load with same intensity or different intensity. So the crack growth phenomena was described thus, and the crack growth was given using this equation. A is the crack length, this is the amplitude of the stress, this is one constant, this are also some constant, but this constant will have a value from 2 to 4, this constant will have a value of 1 to 2, and this is the crack growth, because this is the crack length and this is the number of reversal. So with the number of reversal, how much the crack length is increasing. Then comes the stress intensity factor. Again, the stress intensity factor is very important, because depending upon the stress intensity factor, this type of fracture takes place. Whenever you study about the fracture mechanics, the stress intensity factor is the most important point. So it's given by K, which is again given by sigma root over pi A. It's not coming. K equal to sigma root over pi A, and the maximum and minimum will be like that. Sorry. This is the difference between the maximum and minimum stress and intensity factor. So now let's talk about the graph a bit. This is stage 1, this is stage 2, and this is stage 3. So normally what will happen? Up to certain point there will be only elastic deformation, and the elastic deformation which has been recovered with each reversal. After some point there will be plastic deformation which cannot be reverted back. After some time the plastic deformation will go very rapidly, and that will go up to the rupture point. So after some time you cannot control the things really, it will just rapidly get the fracture point or go to the fracture point. So in this graph also same thing is happening. So in case of 1, it's known as threshold. So this up to this limit, it's the threshold limit. because there the bonding was present and there is no observable crack growth, so it's known as the threshold. Below this threshold, the cracks are non-propagating. So you can say the crack or the elongation of the material is in elastic limit, and the void nucleation may take place, the void coalescence may take place if there is already a pre-existing crack, which should not be the case, should not be the ideal case. But even if it is taking, if it's present, it will not propagate. So this is what known as non-propagating crack below this alpha, sorry, delta KTH, because it's the threshold stress intensity factor. After that, the crack will propagate. So it's a kind of linear region where the crack is not propagating, but the crack growth is taking place. So the void nucleation is taking place, the void coalescence is taking place, the crack is being generated. It is growing, but it's not propagating that much. It's just nucleating, it's getting nucleated. After some times, when it's going to the stage 3, there a rapid crack growth will take place. As I said, after some times now, you can say this region is the plastic region. The elongation cannot be recovered, and with along with the elongation, with each stage, with each reversal, the void nucleation is taking place, the crack is getting formed, but the crack growth is not that much. Crack growth will take place using this formula. This again another power law, and this m is the slope, which is not that much. And after some points now, the plastic growth is so high that it's not in our hand, we cannot restrict the growth, it will just go up to the rupture point, and there the growth is somewhat like this. This is stage 2, this is stage 1, and in case of stage 3, the growth will be like, what is R here? Can anybody tell me? And what is KC?
Ma'am, this is a stress ratio.
Yes, R is the stress ratio, means min by max, and KC is the critical. After which you cannot control the fracture. Okay, so this was up to the week 11 lectures. This fracture behavior, fatigue fracture, and this graph will again be discussed in the week 12 lectures, but those were a little bit more complicated. So just listen to the lectures, and then we'll come back to the next or last doubt clearing session on 17th on week 12 classes. Before that, we'll be having the extra class either tomorrow or day after tomorrow, I don't know. You'll be confirmed through the mail, and even if it's on tomorrow, we'll start the class from 6, no problem. uh, I have put the timing as 5:30 to 7:30. So you'll get the mail for 5:30 to 7:30 for tomorrow if you are getting. But you can join from 6 o'clock. So we'll start from the 6 o'clock tomorrow if you get the mail. So if you have any further question, you can ask.
Ma'am, can you please explain the hysteresis loop once again? Uh, That you have already explained, ma'am. Please explain it once.
Okay. So hysteresis loop means you just imagine you have a crack. Okay, I am giving you some other examples so that you can understand the hysteresis loop. So you are having this crack. Okay, now you are giving some tensile loading. So it will grow like this with a sharpening effect of the crack. And after that, if we are going for some compressive stress or compressive loading, it will be blunted. The tip will be blunted. You can imagine something you are just pulling and then suddenly you are pushing, it will be blunted. After some times you are again pulling it, it will not be sharpened again. The sharpening will not be that much. It cannot be like this. If this is stage 1, this is stage 2, this is stage 3. In stage 4 you are again pulling it. In stage 4 the case will not be equal to stage 2. The stage 4 can never be equal to stage 2. The thing will propagate like this only. If this was the thing previously in stage 3, in stage 4 it will propagate with the blunted tip. And in stage 5 you are again, so it will be like this. You are again compress it. So you see, although you are applying some load like this, but you are not having the similar effect inside the material. So if you are applying load like this, the tip will be like this. When you are applying load like this, the tip will be like this. Ideally it should happen like if you are giving load like this, this one, the tip again should look like this, but it should not, it will not happen, it can never happen. So this is why when you expose the material under the fatigue test, it will never behave like the exact way the load is behaving. The load is behaving with the exact same curves, but the material will not behave with the same nature with each reversal. It will change its behavior with each reversal, and this is why it will go up to the rupture point. Otherwise, it will never go to the rupture point. This is what happens in case of hysteresis loop. Here the hysteresis loop is discussed in terms of the stress and the strain which are being developed inside the material. But in case of any type of behavior of the composite also, the material will not behave the exact way with each reversal. So this is what happening. With the stress, the strain is increasing. With the stress, the strain is decreasing, but it's not coming back with this way, it's coming back with some other way. Again you are increasing the stress will increase, but it will not increase with this way, no, it will increase in other way. Again your stress is increasing, it will increase with some other way. Like this it will happen, it can never be with the same loop. Now you understand what I was trying to say.
Yes, ma'am, I am able to understand. But it is getting widening. Means what is the reason of it? If it is getting widening loop.
So the strain that you are providing, that is constant, that is dependent upon this value, the strain that you are providing. But the strain means the dislocation movement, the slip plane movement, all those stuff. The strain which is happening inside the material can never be the same, because there will be effect, there will be the effect of the fatigue. So this is why uh, loop, there will be a hysteresis loop in case of the fatigue. There will not be the same path. It will not follow the same path. And with each reversal, if you are applying some stress, the thermal stress inside the material will also develop. The stress you are, there is two things, okay, one stress is you are providing, one stress which has been developed inside the material. The stress you are providing is basically the load you are providing. The load you are providing and the result is strain. And due to the strain, the stress is developed. But the stress which are getting developed inside the material will be more and more with each loop, because the strain which is being developed inside the material will be more and more with each loop, although you are providing the same strain, because there will be elastic and then plastic and then will go up to rupture. Na, you understand what I'm trying to say?
Yes, ma'am.
So this is why the thing will be widening up.
Ma'am, it is just like a strain hardening phenomena. Like for every strain, there will be another high strain.
Okay, see, up to certain point you can say that it will be strain hardening phenomena, but after some times now, what will happen? This thing will not be adding some strength or hardness in the material. The strain will be so high that there will be plastic strain. Plastic strain means there will be elongation in the material, and the elongation, when elongation is taking place, means there is no hardening effect. Is it fine?
Yes, ma'am. And this loop is always a closed loop. Like
Yes,
means
these are the
this loop
closed loop,
might.
obviously, because with closed loop only you are applying the thing, na? This thing, this the closed loop load you are applying, na? There is no separation between two waves. These are continuous waves. So as these are continuous waves, so these will be some closed loop. Understand?
Okay, ma'am. Okay, ma'am. Ma'am, I had one doubt regarding high cycle fatigue and low cycle fatigue.
Yes.
So let us take example, ma'am. Basically, I am not able to relate the application of these two fatigue, right? But let us take example like pressure cooker, pressure vessel. If we have a pressure cooker like at home, and if we are designing the steam boiler like in power plant, so if we take example of pressure cooker and steam power plant, in which case we will go for high cycle fatigue, and which case for low cycle fatigue, or both are high cycle fatigue.
Okay.
Means
Steam pressure cooker and another one is steam boiler.
steam boiler, because ma'am, actually when I was studying some literature review in regards of my topic,
Hmm.
so somewhere they have taken low cycle fatigue and somewhere they have taken high cycle fatigue with the same reinforcement and same welding process. So that's what I confused. Means sometimes they are checking high cycle fatigue for aircraft wing, if the aircraft is flying and then wing is subjected to high cycle fatigue, and sometimes they have taken the same thing as a low cycle fatigue. Means how to choose according to the application. Basically, I have these doubts. Means if I will
In
be asked
okay,
like.
in research, whatever I have seen, I don't have much knowledge in this area actually, that whether to choose low cycle or high cycle. But whatever I have found in literature is, in most of the cases, people go for the low cycle fatigue because it consumes less time, because fatigue test takes a lot of time. So in case of research, and if you are a PhD student, in most of the cases we go for the low fatigue test, because ultimately it will give the curve. And for high cycle it will take a lot of time. But again, if your application is telling you that the stress which will be generated in the machine will be very high, then you should go with the low cycle fatigue. But at the same time, you cannot know that what is the high stress and what is the low stress for a particular component. Maybe for some component 10 MPa is low stress, but for some component which is having low dimension, the 10 MPa stress is very high stress. So this high, low, these terms are vague terms, na? It's nothing. You cannot say like yes, 100 this value is high and 10 value is low. I'll say 1 value is low and 10 value is high. So it's dependent upon that which type of uh, test you want to do for your sample, depending upon your application. If you believe that the aircraft wheels which will be exposed with a very high stress because it needs to bear the whole aircraft, so we'll go for low fatigue test. But you can also go for high fatigue test to see, because on the aircraft wheel is also designed in such a manner that it should bear that load of the whole aircraft. So it has that strength also. So you can go for the high cycle fatigue as well, because if you are designing one aircraft that should last for a long time, so it should have a very high number of cycles to failure. So I will go with the high cycle fatigue to see how much maximum stress is it can bear, because already I have designed my wheel in such a way that it can bear that high stress and high load of the whole aircraft. But for research, for time constraint, we basically go for the low cycle fatigue. So I think means I believe this much only I know about this thing. Hello, Sailesh, you are not audible. You are muted. If you, I think you are muted. Either your net is not working or something. I don't know. If you have any further doubt, you can mail me regarding this high cycle, low cycle. But before that, I'll recommend you to go through the other lectures of week 12, because after that you may have other doubts as well. So let's see the previous year assignment for week 11, and then we'll wrap up today's class. Actually, I'm also not well today, so that's why I want to wrap up quickly today. If you don't have any further doubt, just see the questions. If you have any further doubt, you can mail me anyway. So the first question you can see, you can answer. Please answer, any one of you.
Ma'am, I guess all three are correct.
Which of the following statements is are correct? Any one of, okay.
Ma'am, I guess again the three of them are correct.
Yes, 2 and 3 are correct. Did you answer it?
Ma'am, I didn't get like the first one isn't it correct, ma'am?
Matrix yielding in brittle matrix material leads to stress. Okay, there is no scope of stress relaxation in case of brittle yielding, because brittle yielding takes place very fast. It will just be like after some points it will fail. But in case of ductile, it will have that time to get that relaxation by propagating the crack or by nucleating the void and those stuff. But there is no significant time for this type of things in case of brittle. So there will be no stress relaxation. It will just break after some point if the load is very high. Understood?
Yes, ma'am. Understood.
please.
Increase in particle size.
Yes. Next question is two statements are given.
Mom, I guess one is false and two is true.
Uh, why? Why is it so? It's both the statements are false. No. For brittle matrices, failure to of a single fiber does not propagate through the entire composite. So failure of a single fiber, it will not be like failure of a single fiber and does not propagate through the entire. It will fail at a time. At a time, all the fibers or all the fibers present over that particular path will fail. There is no propagation. There is no chance of the propagation of the fiber.
Yes, ma'am. Like the first one is false. Ma'am, with the second one, weak interface bonding does not relax the fiber in the brittle matrix and leads to rapid crack propagation.
No, ma'am.
Isn't
Weak
it correct?
interface bonding does not relax the fiber in the brittle matter and leads to rapid. Does not relax the fiber in the brittle matrix. Yes, it's true. And leads to rapid crack propagation. Yeah, it should be true actually. The statement true. True. No? Okay.
Yes, ma'am.
Yeah, I also
Just
feel this should be true. So statement one is false, but this is statement two. Then it's which of the following statements is are correct about the growth of large size crack under tensile load in the fiber direction?
ma'am, the second one is true.
Ma'am, I think first.
It's both. There is failure in both fiber and matrices. If interface bonding of fiber and matrix is weak, then crack front is non-planar. So both the things are true now. The next one is in ductile materials, the plastic deformation before fracture. It's much larger than the elastic
Yes,
deformation.
ma'am.
Actually, it is first and second.
Yes,
It is first and second is true.
yes. Then failure surface of DRMMCs with ductile matrix will show.
Ma'am, I guess all the three are correct.
All
Yes.
are correct.
Then 9.
Ma'am, one and three are correct.
Yes. One,
Ma'am,
yes, one and
Ma'am,
three are correct, but this boxes have come down.
okay.
So next is pick the correct sequence.
Ma'am, is it the second option?
Yes.
Yeah, first, second.
Yes. So this is all about today's lecture. If you have any further doubt, you can just mail me. No problem. Otherwise, we can end today's class a little bit early today. Okay. Thank you and good night.
Thank you, ma'am.
Okay, ma'am. Thank you, ma'am. Thank you.